Hello guys, so we are going to continue the discussion with respect to statistics, and in this video we are going to see about a new distribution which is called as binomial distribution. Already in our previous video we have also understood about Bernoulli distribution. Now let's go ahead and first of all see the definition of binomial distribution, and I've taken this definition from Wikipedia. The entire credit goes to Wikipedia along with the diagram, along with the definition. Okay. It is always a good practice you try to see Wikipedia, because over there the content is quite precise and you'll be able to understand things. So over here in probability theory and statistics, the binomial distribution with parameter n and p. Okay, there are two important parameters n and p. It's a discrete probability distribution of the number of successes in a sequence of n independent experiments, each asking a yes or no question. Okay. So here you have a success of n independent experiment, each asking a yes or no question, and each with its own Boolean valued outcome, success with a probability p or a failure with a probability q, which is equal to 1 minus p. Okay. Now here you are just seeing that just by the definition, right? You're saying, hey, it is a sequence of n independent experiments, and for every experiment the outcome is yes or no. The best example will be like tossing a coin 10 times, right? So in short, binomial distribution, if you probably read more about it, a single success or failure experiment is also called as Bernoulli trial or Bernoulli experiment. And a sequence of outcome is called as Bernoulli process for a single trial. That is n is equal to 1. The binomial distribution is a Bernoulli distribution if this n is equal to 1, right? So it's like binomial distribution is nothing but it is having multiple Bernoulli distribution, right? With respect to the outcome, zeros and ones. So in short, I can also define in a simple way, binomial distribution is a group of, you can probably say that if I combine a group of Bernoulli distribution in sequence whose outcomes are either zeros or ones, then I can call that as a binomial distribution. Now, since we know that the outcome is like yes or no, it is again a binary outcome. So obviously we also need to use a probability mass function to construct this specific diagram. Okay. Now let's go ahead and discuss some of the important things. The reason, again, binomial distribution, as you know that for each and every experiment, the outcome is zeros and one. So specifically, we are also working on discrete random variable. So binomial distribution, specifically, we are working with discrete random variable, right? This next important point is that every outcome of the experiment is binary. Next important point. These experiments are performed for n trials. As I said, n trials. Here we can see that we basically work on sequence of n independent experiments. So here, that is the reason we are saying that these experiments are performed for n trials. Okay. One of the example can be tossing a coin for 10 times. Now, you know, tossing a coin, if I just consider this as a single experiment or single trial, here my output is heads or tail, right? So the outcome is binary, right? But when I am tossing it for 10 times, so my n is equal to 10 value it becomes, right? That basically means I'm working it for n trials. Now, before I go ahead and probably show you multiple examples, let's first of all write some important notations that are used over here and what are the parameters that are specifically used. Okay. And then we will talk about the formula, how to construct this PMF, that is probability mass function and all. Okay. So here you can see PMF. Here, if I say my probability is 0.5 and n is equal to 20 trials, I will be getting this blue color, something like this. With respect to p is equal to 0.7 and n is equal to 20, you will be able to see over here. So, and with p is equal to 0.5 and n is equal to 40, you will be able to see some distribution that I'm actually getting over here, right? How this distribution is basically constructed, for this we use a PMF function, and for PMF function of a binomial distribution, the formula looks a little bit different. So first of all, we need to understand the notations. So the notation for binomial distribution is denoted by b, n, comma, p. Now, first of all, we'll understand what is b. Okay. So let me just go ahead and define the parameters. So first of all, n, I will go. It belongs to 0, 1, 2 to some value. This is nothing but, this is my number of trials. Number of trials or experiment. Right? Understand what exactly is binomial distribution. I am performing an experiment multiple times and the outcome of every experiment is 0 or 1. Right? The outcome is binary. Like I'm tossing a coin 10 times. So for every toss, I may get a head or a tail. Right? And if I'm tossing it for 10 times, so that basically becomes my n value. Here, my p value, it belongs to 0, 1. Okay. This is nothing but, this is my success probability for each trial. For each trial. It's like when I'm tossing a coin every time, I may get heads or tail. I may denote it as zeros or ones. Okay. Then if you know p is this, then q will be what? 1 minus p. Now, additionally, there is a one more support parameter that we specifically use. And this support parameter is nothing but k. And it belongs to nothing but 0, 1, 2, 3 up till n. And what does this basically mean? It shows number of successes. Number of successes. So number of successes, if I'm tossing every coin, let's say if I say tail is a success, right? How many number of times I may get tail? For n time, max to max, I can get n successes, right? So number of successes is basically denoted by k, you know? So number of successes basically means when I'm tossing a coin, I'm probably getting tail or head, which may be a success for me, right? So for every trial, like how many number of successes can I achieve, right? For n trials. So I can basically achieve n successes, right? So considering all this parameter, we will go ahead and take the PMF and we'll see that how we can construct this PMF. So for this PMF, we will go ahead and write probability of k, and PMF is nothing but we are just trying to find out the probability. For k, n, p, we will define like this. It is nothing but n ck, this is nothing but combination, p to the power of k, 1 minus p, n minus k. This formula, I hope you know that, right? P to the power of k, 1 minus p, n minus k. If k is equal to 1, you know that if my trial is just 1, right? My number of trials is just 1, n, then I used to replace 1 over here. And this basically becomes a Bernoulli distribution. But since this, we are doing it for n trials. So now my formula looks something like this. N ck, which is nothing but combination, p to the power of k, 1 minus p, and to the power of n minus k. So here, I will go ahead and write for k is equal to 0, 1, 2 up till n, right? K value goes from there to there. And here further, if I take this n ck, I can go ahead and write n factorial divided by k factorial, n minus k factorial. Okay. So this is how we specifically go ahead and compute the first component. Okay. So this is what all the things are there with respect to this PMF, right? And just by using these values of parameter of n, p and k, I will be able to construct this. So I just require p is equal to 0.5, n is equal to 20, and k value will be almost same. Considering all the success over here, I'll be able to see this. Okay. Similarly, if I go ahead and compute the mean of the binomial distribution, the mean is specifically given by n multiplied by p. And variance is nothing but it is given by n multiplied by p multiplied by q. Okay. And if I probably consider standard deviation, it is nothing but square root of npq. Now guys, I am not going to derive this because I feel that this is not that important as a data scientist. You just need to know about the distribution and you need to know the assumptions. Okay. Now this was about all the formulas that we specifically discussed. Now let's go ahead and solve some problems. Then you will be able to understand in a much more better way. Okay. And when I probably consider this is called as binomial coefficient. Binomial coefficient. Okay. Let's go ahead and talk about this. Okay. So let's say I will just go ahead and take an example of coin flip, the basic example. So in coin flip, let's say the number of trials I am performing this experiment for n is equal to 5. The probability of success, as you all know, what is the probability of success for a fair coin? That is my P. It is nothing but 50%, right? So 0.5 since the coin is fair. Okay. Now I'll go ahead and write number of successes. Now number of success is nothing but it is denoted by K value. It can vary from 0 to 5. Okay. Now let me just go ahead and tell you what kind of question may come as a data analyst. What is the probability? What is the probability of getting exactly 3 heads in 5 flips? Now, please observe this. Now you'll be able to understand what exactly all this parameter meant. Okay. What is the probability of getting exactly 3 heads in 5 flips? So here my n value is obviously 5. K is number of success, which is nothing but 3, right? 3 heads I need to get, right? So I'm just going to try to calculate what is the probability of x is equal to 3, right? And it is very simple. I will just go ahead and write phi C3, right? Because I have to use this formula. Phi C n C K phi C3, okay? Then P to the power of K, P to the power of K is nothing but probability is 0.5 to the power of 3. Then I have 1 minus 0.5. Then I have 5 minus 3, right? N minus 3. And if you go ahead and calculate this, you will be getting 0.3125. This is the beautiful answer that you can actually get. And this is the kind of questions that you may get as a data analyst or in any interviews. What is the probability of getting exactly 3 heads in 5 flips? So 5 flips is basically a continuous binomial distribution, right? And for every trial, I'm getting an outcome of 0s or 1. I need to probably find out how many heads we will be able to get it. Okay. Let's take one more example. And this, I have solved this example. Okay. And personally, in my experience, when I was working for one of the company, I visited the factory and it was something about quality control. Okay. Quality control. So let's see this example. So let's say I have a scenario inspecting 10 items in a factory. So let's say you're inspecting 10 items in the factory where each item has a 10% chance of being defective. So what is the chance of being defective? It is 10%. Let me go ahead and write like this. Defective. Okay. Now in this scenario, what kind of questions may come? Okay. So let's say, first of all, here I'm going to just put some information. Number of trials. First of all, these are the information that I have. My n value will be 10. Then probability of success, which is nothing but P. Let's say 10%. So 0.1% is my defective chances. So this is basically my defective item, right? Out of 10. Then probability of success. Probability of success basically means the item being defective. Okay. Then number of successes. Here my K value will be varying from 0 to 10. Right? 0 to 10. Because out of that 10 item, all the 10 can be defective, right? And each item has a 10% chance of being defective. So the probability of success is 10%, but number of success, defective item may come from all the items. Okay. Now my question will be, what is the probability? What is the probability of finding exactly 2 defective items in a sample of 10? Okay. So here my question is that what is the probability of finding exactly 2 defective items? I know my 10% is the defective chance. Each item has a 10% chance of being defective, but I really want to find out exactly 2 defective items in a sample of 10. So if I go ahead and calculate the probability, it is nothing but probability of x is equal to 2. Then I will say 10 C2, right? Then this will be 0.1 square because the probability of success is this. Then 1 minus 0.1 square to the power of 10 minus 2. Same formula. I've just applied this formula and I've replaced all the values over here. And if you further do the calculation, this will be approximately, I've done the calculation, so it will be nothing but 1.937, right? So this is what it looks like, and through this you'll be able to see that how you're able to calculate it. And this is an example of binomial distribution, right? 10 items. If I'm examining each and every item, it can have an outcome of 0 or 1, saying that whether it is defective or not. So I hope you like this particular video. This was about binomial distribution, and this is how the distribution looks like. If I keep on combining this, then I will be getting the cumulative distribution, but the value will be between 0 to 1, right? But I hope you have understood how did you get this probability mass over here on the y-axis. It's just by using this formula, right? So here I have already calculated it, right? 0.13. How am I able to get 0.31, right? So this is how we basically calculate the probability. So I hope you like this particular video. This was it from my side. I will see you all in the next video.